Hi, fifth period. This is Mrs. Mahalik reporting in. It's about 8:22 on Thursday night. Um, and I was just reading my letter from Mrs. Prohaska, and I'm a little concerned about a couple things. So I just want to make sure I'm clearing some things up. So my expectation of you when I'm not there is you should be in your seat when the bell rings. You should be in your seat, not standing around, and then you should be ready to do what you're supposed to do. And so today or yesterday, sorry, Thursday was probably not your best example of the way that we want to show that we behave. So hopefully we're going to be able to prove that we can behave appropriately when Mrs. Mahalik is not in the classroom. So hopefully that's something we're going to work on. So the first thing that you were supposed to do was you are supposed to go onto the eCyber Mission website and complete that survey. And it appears that most of you completed it in about 10 minutes, which is a little concerning because the survey is supposed to take between 30 and 40 minutes. So I'm interested to see how those results turn out. The second thing that you were supposed to do was to go on this document and you are supposed to read it and then share why those answers were the correct answers. Um, and I'm not sure that people really did that. And so I want to make sure that you do that. But in order to avoid what happened today, which was mainly you wanting to play on your phones and then getting kind of loud and rowdy, I've set it up so that that doesn't happen. So we're going to do some math problems together. And then once we do some math problems together, I have a video for you. And it's on Newton's laws of motion. And you're going to be required to take 20 facts from the video. All right. So that's the way that we're going to handle the situation. So hopefully this is something that you did because it's going to be really, really helpful to you. Um, but what we need to look at now is this, which is kind of actually weird. Like the color, it's blue, but if that'll work. So what I want you to do is go ahead and pull out P from your packets. Ben, do you have any idea why this just turned green or bluish? This document camera. Oh, there it goes. It just fixed. That was weird. That was really strange. Okay, so what we're going to find with Newton's second law of motion um, is that it's kind of a continuation on Newton's first law of motion. So Newton's first law just says that objects are going to stay at rest or objects are going to continue to move unless there's a force that acts on them. The force that we typically see here on Earth is the force of friction, and that stops things. But Newton's second law relates to how the objects move when they're not balanced. Okay. And so what we have here is it says the second law states that the acceleration of an object is dependent upon two variables, the net force and the mass of the object, which we kind of talked about a little. That an object that's very, very big is going to be harder to move than an object that is small. All right. And so what this table over here shows you is that when forces are unbalanced, acceleration can't be equal to zero because that would mean that it wasn't moving and that it's dependent on force and mass. And so there's a couple different ways that you can write the formula. The formula that you see here is the same formula that was in your book from the notes that you took. Acceleration equals force divided by mass. Um, and then the other formula is force equals mass times acceleration. And that's typically um, what you'll see me do. So what I want you to do right now is based on what we just talked about, I want you to answer those 6 questions. So Mrs. Prohaska or a student, you can just pause this video and we'll pop back in and go over the answers here in a second. So go ahead and pause the video. I want you guys to answer the critical thinking questions, part 3, 1 through 6. Okay, so our very first question here is what two variables is acceleration dependent on? Well, acceleration is dependent upon the two variables right in your formula here. So the two variables that we're dependent on is force, and just remember that that's a net force, which means the total force, and it's also dependent on mass, okay? So that's important. Then it says, what's the relationship between these variables and acceleration? So I want to know what happens to acceleration as the force increases. So as force increases, if your mass stays the same, what is going to happen to your acceleration? And so sometimes it's easier just to like plug some numbers in there. So if I have a force of, say, 10 newtons and I have a mass of 1, then my acceleration is going to be 10. But if I increase the mass, um, if I increase the mass, sorry. Great. So if we're talking about the two variables that acceleration is dependent on, it's going to be the two variables up there in the equation. So force and mass. All right. The next question is, what is the relationship between these variables and acceleration? So it says if you increase one variable, what happens to the acceleration? So first, we're going to talk about increasing our force, okay? So if we increase our force and we keep the mass the same, then what happens? So sometimes the easiest thing to do is just to plug some numbers into the formula. So if I plug in a force of 10 and I say that my mass, which we're saying is going to stay the same right here, and I keep it at 1, then my acceleration is 10, right? So over here, say that my force is 100, my mass stays exactly the same, well then my acceleration is 100. So as force goes up, mass stays the same and acceleration goes up. And that should make sense. If I exert if I'm talking about Donnie and I exert a force on him, then we'll have an acceleration. But if Mr. Mahalik exerts a force on Donnie, his force is going to be a lot stronger than my force. And so the acceleration on Donnie is going to be a lot higher. Okay. So the next thing we want to look at is mass. So if we increase the mass, what happens to, oh, sorry, that's a lie. I'm distracted by the family around me. Oh yeah, sorry, that is right. So if we increase the mass, but we keep the force the same, what is going to happen? So same scenario. Say I have a force of 10 and I have a mass of 1. Well, my acceleration is going to be 10. But if I keep the force the same, 10, and I increase the mass, the acceleration is going to be lower. Example here, I take Donnie and I use a force and I push him and I have this acceleration. But in this scenario, I have a force and I push Mr. Mahalik, he's going to accelerate less because I'm not as strong and he has a heavier mass. So acceleration is going to go down. Next one. If an object is not accelerating, what can you determine about the sum of the forces on the object? So if an object doesn't accelerate, what can you determine about the sum of the forces on that object? Well, if it's not accelerating, then the forces have to be balanced, right? So we already talked about this. This has to be a balanced force. Moving on to number 3, if the net force of an object is in negative direction, what would the direction of the acceleration be? Well, that would have to be negative. That's like when we were talking about vectors. Oh, sorry, you can't even see that. When we were talking about vectors, we were talking about moving towards something or away from something and that being negative or positive. Number 4, if you double the net force on an object, what is the resultant acceleration? So let's go back to the Donnie example up here. So we have, oh, we're doubling our force. So we have this force divided by the same mass and our acceleration. So if I double the net force, what happens to the acceleration? It squares. So 10 times 10, or times this by itself. If you double the mass of the object while leaving the net force unchanged, what is the resulting? So we can look at this one. We can look at this Donnie situation right, oh, can't see that anymore. This Donnie situation right here, we're going to double the mass. So it's 10 over 2, and so that would be 5. And so in that case, we would be halving. And last but not least, a Cadillac Escalade has a mass. So these are example problems. So remember, write out your variables. Force equals, mass equals, acceleration equals. A Cadillac Escalade has a mass of 2,569.6 kilograms. The acceleration is 4.65. What is the net force? So force equals mass, 2,569.6 times acceleration. And so when you multiply those together, hopefully you should end up with a unit that is in newtons. And I'm pulling out my phone here real quick to get that math for you. So 2,569.6 times 4.65. That's going to be 11,948.64 newtons. Okay? So what I want you to do today is I want you to do these questions 1 through 5, okay? So you're going to take your given. Given will be F equals M equals A equals. You'll fill them in, and then you'll put your work. So something that you may want to write down is some units. So maybe at the bottom of page P, we should write down some units. So the unit for force, which we abbreviate as F, is going to be a Newton, which is abbreviated as N. Our unit for mass, which we abbreviate as M in the formula, is going to be a kilogram. And acceleration is meters per second squared. So if as you're reading through the problems, you're struggling like, what is F? You can just look and say, oh, this is measured in kilograms. So if it's measured in kilograms, kilograms has to be mass. And so that would go there. Okay? So you're going to do these 5. I want you to take a picture and upload it, just like, we're going to start doing. And then I want you to post any questions or problems that you have. And also, I want you to watch this video that I'm going to also upload. So if maybe Mrs. Prohaska, give them like 5-10 minutes to work on this. And then at about 10 minutes, pop on that video that I'm going to put on here too. And so we'll go over this tomorrow and we'll do a couple more practice problems, but this should take up your whole period. So hopefully you guys are having a good day. Hopefully today's better than yesterday. And we will see you shortly. Have a good weekend. Bye.